everyone. We are the next speaker. There's three of us. I'm Torkel.
I'm Vaibhav.
I'm Utkarsh.
And we're going to talk about, well, do you want to start the introduction?
Yes.
Should we do add a clicker?
Why? No, I think it's fine. Okay. Hi everyone. I'm Vaibhav Dixit. I'm a software engineer at Julia Hub, and I'm going to be joining the Julia Lab here at MIT starting next month. So what we wanted to do today was just sort of, I mean, last time we had a JuliaCon physically was 4 years ago, as we have been talking about since the day one. And since then, SciML, both as a software ecosystem and as a field, has sort of just taken this huge explosion, right? I think at this point we have around, I don't know, at least more than 50 packages, right? And a lot of things that you want to do with tools, it's often, even based on the feedback we were getting in the Birds of Feather on systems biology earlier today, it seems like there's some disconnect in terms of what's available already in the ecosystem and just in terms of users not being aware of it. So just to give a sort of sense how much of an impact SciML is having, right? All like these are, you can see like very distinct fields like geoscience. There's like, I don't know, there's physics and epidemiology and stuff like that, right? And all of them are using the same software stack and same like very similar techniques. So I think that's like a very unique, a very unique situation we are in. And I don't think there was this sort of sharing of tools and techniques across these different fields before. Cool, and we have been talking about this, like even in the keynote, Chris sort of covered it. What actually enables that to happen, right? Is it just that, differential equations.jl is like the fastest solver of differential equations out there, and then we just put neural networks in there, and that's why SciML is SciML? Well, kind of, but then there's other things also, right? I mean, you need sort of this support of various, what used to be very separate verticals in scientific computing. You want to be able to sort of support very different architectures, right? Someone will just want to run experiments on this laptop. Someone will want to use GPUs or even, I don't know, TPUs or something. So you want that. You want very fast solvers, not just for differential equations, because differential equation solvers don't exist by themselves, right? You need linear solvers. You need nonlinear solvers. So you need a robust ecosystem where you can swap in all these parts that make up the entire solver domain, right? And then for users, what really matters is how you write out the models, right? We used to have this functional interface, but now we are moving towards a symbolic interface with modeling toolkit. So modeling domains requires some domain-specific languages, and we have, I think, gone a long way just with modeling toolkit for it, but also some other very much more narrow focused DSLs, which you'll be able to see later. And then also, obviously, the ML in SciML, right? You need machine learning libraries, you need optimizers. And then because you're not dealing with you're not just fusing together linear functions, it's not just neural networks, it's actually much more complicated likelihoods when you're dealing with these SciML architectures. You don't want to just rely on the traditional machine learning optimizer. You need a way to be able to experiment with different things. You might even want some uncertainty quantification, so you need ways to solve Bayesian inverse problems and everything. And then you need to be able to analyze results. Like that's sort of obvious, I guess. So all of these things have to work together with an interface that sort of works together, right? It can't be that a user has to go and learn each of those separately, and then, yeah, that's too much of a learning curve. So why is Julia and why is SciML? Well, if you missed that, it was like, why is Julia SciML specifically suited for it? That's because we have all of those. And as I said, right, we have grown to this large organization. We have a lot of packages, and this is not comprehensive at all. Literally, I think I know at least 4 or 5 packages on the top of my head, which are not here, but that was sort of a limitation of the space and just in terms of the expertise we 3 shared and couldn't cover everything. So I'll hand it off to Torkel, who will be covering some of the modeling tools available, and then maybe, and we'll also be interleaving our sort of, we'll be walking over the ecosystem basically, and we'll be interleaving that with some demos and some code examples that you can see.
Does this work? Okay. So I'm just going to want to talk through like a couple of the things which the modeling package is built upon. The first one, symbolics.jl. This is an interesting one because it really, to me, does 2 entirely different types of things. So the first thing, it's a computer algebraic system. So it allows you to represent, say, an equation symbolically. And then, for example, if you then write your equation, you want to take the derivative, it does this entirely symbolically. So it's a very powerful engine in this sense. Second, what this do, it can act as a base for a lot of the tools that builds modeling within the SciML ecosystem. So it means that a lot of the models that you build deep down internally is entirely symbolically represented. And this allows a lot of the tools to do some kind of fancy stuff. For me as a modeler, like I only encounter symbolics in the second sense, which means that practically I never encounter symbolics at all, because it's something that happens deep down. But we think that it can be quite good. Like if you hear about symbolics, this is basically what it does. And next one, modeling toolkit, again does a little bit 2 types of things. The first thing, which again for me is kind of important one, it creates an intermediate representation for representing SciML models. This is typically a differential equation model. And the idea here is that you have 2 types of people doing modeling here, working within the system. You have people like build modeling packages, which creates a model. Then you have people that build tools which does things to this model, say do simulations, sensitivity analysis. And really the promise here in modeling toolkit is that it implements one intermediate representation. If a modeler can create or represent their model using the modeling toolkit way, then they have all of these analysis tools automatically working on the model. In the reverse, if I want to make a new tool, as long as for, say, model analysis, as long as I make my tool work on modeling toolkit type representation, it will have access to all of these kind of modeling packages when they're from electronics or biology or something like that. And I think this is quite a powerful thing within the SciML ecosystem, that we have this representation which allow people from many different domains to collaborate. And then the second thing that Modeling Toolkit does also, it actually allows you to build these kind of models by writing the equation directly. And I'm going to briefly show this in an example. And actually then have various packages which feeds into Modeling Toolkit to allow you to build models. One of them is Modeling Toolkit Standard Library, which just implements a lot of like ready-made modeling components which you can connect. So it can be like a capacitor or resistance in an electronic circuit, and you can just connect them to create your model. So that's one thing you have. Another thing you have is domain-specific modeling languages. So say, for example, I work in biology, I make a typical specific type of biological model, so then there's a packet catalyst for creating these models. There's the orbital trajectories, if you have like, I think, satellites that goes around, and then like there's a specific way to represent these models, and you have these separate packages. But a lot of what this one does is actually like feed in and create a modeling toolkit model, which then connects it to the entire SciML ecosystem. So if so now I'm just like briefly going to show how like these kind of models appear in real code. I think we're going to start with this one. Right. Some slight technical issues, soon sorted out. Okay, very nice. So I want to start with this one. Don't you have the NPC set one? Okay, so there, this is an NPZ model, which is like a very common thing when you model plankton in the ocean. Basically, you model the amount of nutrients, the amount of photoplanktons, Very good. The amount of photoplanktons, and see how these interact. And this creates a very normal, like a differential equation type systems. And here we use modeling toolkit to, so basically, okay, we want to create a model. First, we declare what parameters we have. Here I've simply called my parameters A, B, and C. And then what kind of variables we have in the system. Of course, we have T, it's going to differential equation, depends on time. And then we have some time-dependent variables, and the amount of nutrient, P, the amount of photoplanktons, and Z, zooplanktons. And then we define the differential, a differential. And then what modeling toolkit allows you to do is basically write equation in pure code. So here we have differential equation for amount of photoplankton, which plankton, I think, like gets sunlight and grows. So you see here, for example, there's a growth rate, which is the amount of nutrients and the photoplankton, so normal growth things, times a parameter. And then you have a death rate, D, which is basically to get eaten by the zooplanktons. And here we have like normal death. So this you can do in modeling toolkit. You can do a very similar thing to create a partial differential equation. So here we have x and y, basically like a space. We create a variable u, second derivative with x and y, and then we create an equation, which is the xx, so the two derivatives with respect to x and y. If you add them, you get 0. And then you set your boundary conditions, your domain, so like where the model is, and then in the end, you can kind of combine everything to a partial differential equation system. And then finally, we're showing off so this here you write the equation directly, like one alternative is your domain-specific package, and here you do something, in this case is called Catalyst, and here you create your model slightly different. Here's called a sigma general system, and I'm just going to briefly, like biology must understand what's happened. Here are basically reactions. So we have empty set to sigma, like creation, degradation of sigma, creation, degradation of A1, A2, A3, so this is a variable of the system. And then we write some rates here. But this is basically to show you that if I do a specific type of model, I know more about my system than just the differential equations, and I can actually use this when I create my model.
So I'll be talking about some of the work that we have, like with the solvers. Like, let's say now we have model our system. The natural question is like how we solve them. So basically, the very go-to software for this is like differential-equation.gl, which is like built on a lot of small packages. So let's say if you don't know, let's say if you are working with an ODE, you don't know what solver to use, or like you really are like not very aware about your model. It has like a lot of features, like such like automatic solver choices, selecting proper linear solve methods, which are like built into that, and that's why it's a very quite a heavy repository. But let's say if you want a more fine-grained control, let's say you know now about ODEs, and you know, let's say it's a stiff ODE, or let's say it's a non-stiff ODE, you can use like ordinary DiffEq to solve basically like ordinary differential equations and differential algebraic equations, which are like have like a lot of constraints of the algebra in the mass matrix form. And moving on that, so similarly, let's say if you now know there's some stochasticity involved in your model, then we have some different packages to like basically use to simulate stochastic differential equations. And I think the lastly is like now, okay, now let's say if you know something about the discrete processes, like I think jump processes also covered yesterday, and I think you should visit that talk, which basically do a lot of simulations by Gillespie algorithms of the jump processes. Finally, like some of the things that we have, some of the advanced solvers which are like not really commonly available is also about the delay differential equations, which basically extensively covers like where there's like a lag in your ordinary differential equation model. And bringing this all together, this is like moving across the abstraction that we started from ordinary DiffEq. We have very high fidelity solvers, like building all the stochasticity and the delay differential equation model together. So we have another package called stochastic delay DiffEq equation models. And finally, so we support a lot of, quite a lot of solvers in that, and we also strive to use the solvers which have existed before. So Sundial is one of the packages, which basically is like a wrapper over the C++ differential equation solver library. So CVOD, BDF, like these very common solvers which have like people use. So we provide that interoperability instead of like not, let's say you're suited for some of the optimization tricks which are like done in those solvers. So these are like some of the things that Sundials provide. And similarly, like on the line of, let's say, this is like a more of a high level, on the partial differential equations, like method of lines. So the way to basically like simulate PDs is by generating semi-discretized ODEs. So you can use like method of lines to generate automatic discretizations, which basically convert your partial differential equation model to a ODE or a linear solve, like how you want it. And I think the last thing, basically in this, like a lot of work has been done in physics and for machine learning. And for that, we also have a package called NeuralPDE, which basically allows you to seamlessly integrate a lot of neural networks for solving PDs using pins. And finally, this is the work that I was doing. So I'm going to also share a demo of that. It's like a lot of how can you leverage parallelism for GPUs in this case. So DiffEq GPU basically provides a very high-level interface of like using GPU acceleration in ordinary differential equations, and which is like sometimes may feel counterintuitive because ODEs are a serial processes. So it's like sometimes you need to have like particular like use cases where say you're simulating a lot of ODEs together, or let's say there is a big ODE and you want to like accelerate all the, let's say, the array-based computations on a GPU or CPU. So DiffEq GPU like especially works on a lot of ensemble problems where you're like simulating a lot of small differential equations on a different parameters. So yeah, I'll just show a demo like how basically we're going to solve these, and like basically the demo is very very composable, that we work from a very high level interface. That essentially what we are trying to say is that you can basically bring all the components together, and you don't actually don't need to like write a specific API for, let's say, DiffEq GPU or stochastic DiffEq, something like that. So I have an example set it up here. Maybe I'll just like try to run this if this runs, but yeah, it's already compiled, so you can just see the output of that. So basically, in this case, I'll be using the Torkils model in this, which is like a catalyst model of the equation, and try to basically do a parameter parallel sweeps. So we have this model loaded, and then we basically declare some of the parameters that we have. These like some of the like default parameters we want for the compiling of the model, and then this basically is like a grid, like a mesh of all those points where you basically want the parameters to have. So this model specifically has 6 parameters, so you can see like 6 grid in this case. And now we'll basically just take a Cartesian product in this. So like it will basically like generate 168,000 ODEs, or like stochastic differential equations in this case. Similarly, this is some of a boilerplate code that, okay, now we basically give a function, so like how a new stochastic differential equation will look like. So it will just basically do a remake on the parameters, and then some initial value declaration in this case. Which is like, I think this is like, 4 states. And then this catalyst model can be automatically passed to an SD problem. You just like basically take this model, like the sigma gen system, to pass on that, and then basically we do a modeling toolkitize on that to basically generate a compatible form. But yeah, so I think these are like, so these are the ingredients which are like necessary to basically like start for GPU acceleration, and then basically you declare ensemble problem with the problem definition and things like that. And then you basically like simulate this. So I have a comparison here, like the times are already written. I don't want to run it here because it's going to take about a minute, which will like take some time. So 53 seconds like typically take if you do with ensemble thread, which is like the default CPU multi-threading. And then if you basically just automatically change it to like GPUs, it will gonna take like 14 seconds. So if there's like a 4x speed up instantly, and you are just like working from a catalyst model. If you want more fine-grained control, so this is like not the end of the story, because a lot of overheads are like there from basically transferring from CPUs to GPUs. And lastly, there's like something on lower level API, which I wanted to show in this case, which basically get rid of this overhead by not converting to CPUs. And then you basically see that, oh, it's like, it takes like it's pretty fast. It takes, I don't know, it's some microseconds, which is like around 100 times faster. So this is this basically, yeah. So this basically enables all the GPU acceleration that we have. We started from a very high level model and then like easily can be like break up into just GPU acceleration. So I'm now gonna go back to my slides and then talk a bit about, talk a bit about equation solving. So now let's say you know a bit more about the equations that you want to solve, and let's say, okay, you know you need to do linear solve, or you know something about the model. So we do have like very direct APIs to equation solving. So linear solve, like solving AX equal to B systems, directly provides, and which comes with a lot of preconditional, a lot of extensible like solvers, iterative solver, direct solver, things like that. And similarly, building on that, we also have like nonlinear solves, which basically solve the nonlinear equations. And for computing integrals, like using quadrature techniques or like Monte Carlo estimates, there's integrals.jl to basically compute integration. So now I have a demo which basically says that, okay, now how can you basically step upon these features to like get good simulation times for your example. So I'm gonna show one of them.
Maybe skip it.
Okay.
Do you think?
Yeah. So I'll probably go a bit fast. I think the time is not that much, but yeah. So this is a partial differential equation model, which is, I think Tork will cover that, which is written in modeling toolkit. We provide the differentials, and like this is like the NeuralPDE example, and then we basically write the equations like, okay, these are like the boundary conditions in this case, and then like define the domains, and we basically like now generate a PD system upon that. And this is the discretization level, which grows like n squared, so there will be around 1,000 ODs in this case. And then we also like basically go through the discretization technique, which is like the method of line finite difference technique. But now we basically call the discretization to automatically generate good approximation schemes of discretization, and which now creates an OD. And this OD can be like directly simulated to the solver that you just use. And this is completely tuned, can be tuned by your own. And finally, and like coming up onto that, let's say now you have like, you want to use iterative solvers. So you can just like load linear solve and then use like GMRES methods, which is just like an argument to the solver. And let's say you want sparsity detection, like you want to basically do a lot of Jacobians in this case. So it basically now you want to basically sparsify your Jacobians. You can do like use symbolics to use Jacobian sparsity. And now this basically, I think the times are not shown here, but yeah, this basically will iteratively improve your simulation times. And you can also use like factorization. So like that's like the story that how things are being composed. I am not like, these are not part of a single package. These are composed of different packages. And finally, the last piece that is that, let's say if you want to use precondition, which is like exactly the information that you know about the model, is like you can use incomplete LU in this case by basically providing by using the package incomplete LU. And finally, you have a precondition in this case. Like now, the whole story basically is boiled down so that you can step upon these iterations of the solver and like try to find what works best for your models, and you will see a lot of speed ups, a lot of stability like comes around and like works very seamlessly with the composability that SciML have. Now I'll pass to Vaibhav to basically talk about more high level APIs.
Okay, so we are running very late. So I'll have to probably skip the examples I was going to show, but it will be there on GitHub, so I'll give you the link. Anyway, so now we move on to, so we were able to see how we can create models and solve them, right? So the next thing is basically model calibration. You want to solve inverse problems. So there's I don't know, there's like at least 3 or 4 different ways you can do that, but the simplest way you can do is you can use DiffEqParamEstim. What that does is it takes your ODE or like whatever differential equation problem you have, and it gives you out an optimization problem, which I will talk about in a second, and you can just it's all automatic. The optimization problem is basically from the optimization.jl package. That's a package that we have developed sort of aiming to create API to different, a wide variety of optimization solvers, including global, gradient-based, I don't know, and maybe even we have support for mixed integer linear programs and So it's the sort of the entry point to all of those solvers in SciML. Yeah, though that's basically done through these wrapper packages that live in the optimization.jl repository in the lib folder if you're interested. But anyway, we have at this point I think more than 20, at least 15 from what I remember. So that gives you access to like almost 100 different optimization solvers. And all you need to do is you need to change the second argument to get access to all of that. Jump, you all know what it is, but it's a DSL. So that can be a bit restrictive for some of these problems that we have. So that's why we had to sort of develop optimization. Automatic differentiation is sort of like the backbone of a lot of these things that we are able to do with these packages. It serves as so we have support for at least these 4 different AD packages at this point. And I think Zygote is missing from that. So like there's a bit more as well. And that enables you to do basically the local sensitivity calculations, which live in SciML sensitivity, which is essential for being able to solve these inverse problems. Okay. And then you have DataDrivenDiffEq, which is basically to to recover equations from data. So when you have just a data set and you want to, something very similar to what Miles was talking about yesterday, you just want to recover equations from data. This leverages the sparse identification algorithm, if you have heard of it. And then DiffEqFlux, that's like very essential to the SciML story. That's where these that's the interface to being able to use to compose the neural networks from these machine learning libraries like Flux or Lux to be able to create neural ODEs, universal differential equation, deep equilibrium networks, and everything else. DiffEq base is very similar to DiffEqParamEstim. It's like a very easy interface to solve Bayesian inverse problems. And Turing is the leading probabilistic programming language in Julia, and it's completely composable with the entire SciML stack. So there's a very good tutorial on the Turing tutorials, so you can take a look at that. Easy model analysis was a recently developed package where a lot of these things that I have been talking about so far and will be talking in terms of like global sensitivity analysis or inverse problems, this gives you very convenient APIs to directly use all of that on modeling toolkit models, basically, and sort of uses. It's a completely symbolic interface. Some of these that I've talked about you might have to move out of the symbolic stuff. Yes, global sensitivity analysis for performing global sensitivity analysis. Global sensitivity.jl is for performing global sensitivity analysis, which is basically you're trying to quantify the effect of input parameters on some measure of the output, or even the entire time series of the differential equation if you want. SciML expectation allows you to efficiently compute some moments of the differential equation solves. Structural identifiability is this concept of being able to just use the model structure to infer whether the parameters that you have are going to be something that you can estimate from if you have some data, basically. So basically to deal with overly parameterized models, so it will tell you that, or under parameterized. Bifurcation kit is it's a external package which is for creating these bifurcation diagrams. Dynamical system depends on basically differential equation.jl and provides a nice interface for dealing with agent-based models and such. Plots is plots. Quasi-Monte Carlo, this is useful in cases like global sensitivity or some other place where you have to do some sort of a numerical integration, and this gives you ability to very efficiently generate, and I think also in parallel, very efficiently generate these low discrepancy sequences, which are like supposed to be very good for numerical integration. Surrogates is something. It's the open source equivalent of what Sharan was talking about earlier, but it's like very far behind it. Yeah, it's basically you can create surrogate models for your physical models. Reservoir computing is one of these packages that was developed to support basically eco-state networks and liquid state machines. Cool. I wanted to show a demo, but I don't think we have enough time for it. Oh, why did it not change? But I'll just have to, yeah, I won't be able to run it. But basically, this example, I like this demo quite a lot. What we are doing here is, so this model was special. What happens in this NPZ model, right? The A parameter that you see here, that's actually not identifiable. And it's not identifiable in the sense of structural identifiability. Even the structural identifiability, well, if you run it, it actually tells you it's globally identifiable. But then when you actually run the inverse problem and you try to estimate it with this, even just this, I just used a simulated data set, which should be a very trivial thing, right? Like, but even then you can not recover A basically. So the reason I'm going so much into detail is because this is where the composability comes into play. Now, you can actually run global sensitivity analysis on it, and you'll sort of just see that A has no effect on the output of this model, and that's why you can just parameterize it away. Okay, thank you.